Hello, and thanks for tuning in. My name is Gavin Piccione, and in this video, I'll be talking about some of the work that's being done at the University of California, Santa Cruz. This particular project will talk about subglacial fluid compositions linked to the East Antarctic ice sheet's response to Pleistocene climate cycles. And so to set the scene a little bit, here's a bedrock elevation map of the Antarctic continent. And this project is focused mainly on the low elevation basins beneath the East Antarctic ice sheet. And the samples we'll be talking about in this video are coming from the Wilkes Basin. And these low elevation basins have been subject of some interest in regards to global mean sea level, because recent research has shown that they might melt more readily than we previously thought. So these two figures are from two recent papers. This middle one is from Mengel and Lieberman in 2014, and their models show that the ice volume in Wilkes Basin is in large part regulated by the ice near the grounding line, which they show here in red. And that during warming periods, perturbation of this ice near the grounding line could cause runaway ice sheet collapse. And so, looking to some data from the rock record, this figure from Wilson et al. In 2018 looks at sedimentary drill cores from offshore Wilkes Basin and sees with several proxies that indeed the Wilkes Basin does melt in response to warm periods in global climate. So based on these data, we know that Wilkes Basin does respond to climate and does melt during warm climates. But the timing, duration, and magnitude of this response is still uncertain. So this brings us to some of the work that we're doing at UC Santa Cruz, and we're looking specifically at subglacial precipitates as new climate archives. So this is an example of a precipitate that forms beneath the ice in the East Antarctic ice sheet. This formed beneath the Wilkes Basin ice and was collected at Elephant Moraine. It was lent to us by the Polar Rock Repository at Ohio State. And what you see in this sample are interbedded layers of white and dark. The white layers are opal, the dark layers are calcite. And the main observation of this talk will be that Opal-Calcite transitions in these precipitates are directly recording the East Antarctic ice sheet's response to global climate. But before I jump right into the data, I just wanted to take a second to go over the depositional setting of these precipitates and how they get to the surface. And so in the topographic lows beneath the East Antarctic ice sheet, we know from remote sensing that there can form large lakes and channelized systems that connect these lakes. And in this active hydrologic system, we get chemical precipitates forming. And as the ice sheet flows over some of these aqueous systems, it plucks up sediments and these precipitates and entrains them within the ice. And when the ice abuts up against a topographic high point in the bedrock, in the case of the Wilkes Basin, it's being shoved up against the transantarctic mountains, you get ice loss. And in areas where you get ice loss from sublimation, we have blue ice forming. As a response to this ice loss, all of the sediment that's entrained in that ice is left in the surface, and we get supraglacial moraines. And that's where these chemical precipitates are found. And so our main way of characterizing these chemical precipitates is with uranium series geochronology. What we've done is gone through and measured the age of each of these opal layers within this particular precipitate here. And this figure on the right is an age to depth model that we've calculated with Bayesian statistics. On the y-axis, we have depth. On the x-axis, we have our uranium series age. And the main takeaway, just from looking at this plot briefly, is that where we have thick opal layers down here at the bottom and up here at the top, those opal layers are forming slowly. They represent a lot of time. And they're also mainly clustered within MIS 6 and MIS 8, which are global cold periods. And where we get thick packages of calcite in the middle of the sample, we have rapid deposition relatively, and they're mostly clustered within the interglacial MIS 7. And so just with our simple age depth model, we're already seeing some correlation with climate. And so to take that a step further and to define a record of precipitate mineralogy versus time, we use energy dispersive spectra, or EDS elemental maps. Here's a map of silicon versus calcium, silicon in blue, calcium in purple. Those represent opal and calcite layers respectively. And we take line data across these mineralogic boundaries from this EDS map, and we are able to have a time series representing mineralogy versus time. So in this case, we have silica weight percent. So in areas where we have high values on the y-axis, those are our opal areas. In areas where we have low values on the y-axis, those are our calcite areas. So this graph is representing our mineralogic transitions with time. And so to explore a little bit about how these correlate with global climate, we can plot these against global climate records. So in this slide, I have that same precipitate mineralogy record, and below it, I have a record of changing global temperature from the Vostok deuterium record. And as you can see, just by visual comparison, we have a pretty good correlation with where we have opals, high silica weight percent versus cold time periods, and where we have calcites, low silica weight percent versus warm periods in the global climate record. So to quantify both the phases and the correlation of this record, we use wavelet transforms, in this case continuous wavelet transforms, for both records, and then we correlate the two with semblance analysis. And so the results can be shown here. On top, we have the continuous wavelet transform for our precipitate record. In the middle, we have the continuous wavelet transform in the Vostok record. And what may jump out at you is that for both records, we have long period wavelengths. Those are our 100,000 year cycles. And shorter period wavelengths are 40,000 year and 20,000 year cycles. And when we do a correlation, we can see that we have a very good correlation between times where we have opal and cold climate periods and calcite and warm climate periods, both on our 100,000 year cycles, our 40,000 year cycles in most cases, and our 20,000 year cycles. And so this is our first major conclusion, that with our subglacial precipitate record, and specifically the Opal-Calcite transitions, we're actually recording East Antarctic ice sheets' response to global climate. And we can use our wavelet analysis to show us that both records are showing East Antarctic ice sheet responding to orbital cycles. And so for the rest of the talk, I'll be presenting some work we've been doing to identify a mechanism where opal can form during glacial periods and calcite forms only during interglacial periods. And so to do this, we first geochemically characterize our opal and calcite layers to get an idea of the waters that form them and to ultimately inform our geochemical models. And then the second process is that we'll use the Freak software to explore conditions under which opals precipitate and calcite do not. And so as an example of our geochemical characterization of opals and calcites, here are some laser ablation maps. In this case, we're mapping cerium star, which is a way of showing our cerium anomalies. Cerium is a redox sensitive rare earth element. And so in oxidizing water, cerium will be depleted. That will be a cerium star value below 1. And in reducing environments, you can cause cerium to be enriched because you may source cerium from cerium-rich phases. And so as we can see, we have a really good correlation with low cerium star values for calcite, high cerium star values for opal. And so what this is telling us is that calcite is precipitated in oxidizing waters, while opals are precipitating in more reduced waters. Now we have many other parameters that point to this. We don't just look at cerium star. We have iron manganese ratios, arsenic, and then zanes on arsenic and uranium that all point to changing water redox on glacial interglacial timescales and tell us that the opal precipitating fluids are different from those precipitating calcite. Now, as I mentioned, we want to build geochemical models to describe these systems. And the first step in doing so is to identify a subglacial water composition to start off with. And to do that, we've used bulk rare earth element compositions of both opals and calcites. And in this ternary plot, I have plotted the bulk rare earth element composition of opals in the blue circles, calcite in the black circles, and then we have representative compositions of other waters in order to compare with our opals and calcites to get the best starting water composition. And what you may notice is that in these yellow X's, we have Lake Vanda waters. And for the most part, our opals and calcites plot near the Lake Vanda waters. And so a conclusion we're making based on these data is that our opals are forming from a calcium chlorine brine, similar to Don Juan Pond and Lake Vanda bottom waters. And so we're going to use these Lake Vanda bottom water compositions as initial water compositions for our freak models. Here is the first model that I had mentioned. And here we're going to identify conditions under which opal precipitates and calcite does not. And so starting with our calcium chlorine brine, we're plotting the mineral saturation indices on the y-axis and the percent cryogenic concentration on the x-axis. So that's percent water frozen. And this is simulating going from a warm period to a cold period where we would expect opal to precipitate. And as you can see, as we get to more percent of the water frozen in our aqueous system, we drive the amorphous silica, or the opal saturation index, above our precipitation threshold, but we don't have enough bicarbonate in this calcium chlorine brine to ever precipitate calcite. So here we actually are successful in identifying conditions under which opal precipitates and calcite does not, and it takes starting with a calcium chlorine brine and freezing at least 55% of the water. So to take this a step further, we now want to identify conditions under which calcite forms, and we know this should form in response to global warming, or to warming of the system. And so here we start off with the knowledge based on the geochronology and the geochemistry that calcite forms upon mixing of oxidized meltwaters. You have to mix oxidized waters within that. And so we're plotting here saturation index again on the y-axis. And here we have meltwater in the mixture and brine in the mixture on the x-axis. So this is our mixture of our brine and our meltwaters. So as I mentioned, in order to precipitate calcite, the water you're mixing in has to be rich enough in carbon to drive the saturation of calcite higher. And so based on these freak mixing simulations, we predict calcite saturation upon the addition of bicarbonate-bearing meteoric waters, with our highest saturation index mixing in 10% of bicarbon-rich meltwaters with 90% of brine. And this supersaturates the solution with respect to calcite. And this is consistent with textures that we see and the rapid calcite precipitation that we see with our geochronology. And so with that, I'll just leave you with my conclusions. Opal-Calcite transitions in the Wilkes Basin precipitates directly record the East Antarctic ice sheet's response to orbital cycles, as we saw when we correlated our mineralogic transitions with global climate. And then we've identified a possible mechanism based on the geochemical models, which suggest that freeze-melt cycles can drive opal-calcite transitions. And with that, I'll thank my collaborators and our funding sources. Thanks for listening.